welcome to our first official online lecture video for Calculus Math 1431 here at the University of Houston during the spring of 2020. As you guys know, we have a lot of crazy, stressful situations going on, and so if you have arrived here with the time to think about math, congratulations. I am happy that you are able to do so, and I welcome you to continue doing so for as long as you can. Okay, so this set of notes is going to be about what we call section 4.2 in our textbook, and it's the exponential function. So it turns out this is kind of a bad name because there's more than one exponential function. There's actually several, right? Any positive number a we could use as a base, and our variable x could be in the exponent. The most popular choice of a base to use is this one that we call e. It's a bizarre number, sort of like pi. It's approximately 2.718 blah blah blah. And so the function, the exponential function that will form is e to the x. Okay, and so this right here is a sort of basic quick review of some facts from college algebra. Not that all of this should be instantly easily familiar to us at this moment, but hopefully once you look at it you'll realize that it's familiar from what you've thought about. So these two graphs, let's see, I'll try and color code it. One in red corresponds to choosing a positive base a that's bigger than 1. Oops, sorry, I said red, I meant blue. The one in blue corresponds to a being bigger than 1, so that's a equals 2 in this picture. It's bigger than 1. And what you see is an increasing graph. In fact, it's going to go up what we call exponentially. And if you pick your base to be a positive number less than 1, like this red graph shown here, in the graph here when we have a equals 1/2, what we have is a red decreasing graph. And it kind of makes sense. If you think about plugging numbers into the function 1/2 to the x, so I've got g of x equals 1/2 to the power of x. If I plug in x equals 0, I get g of 0 equals 1. If I plug in x equals 1, I get a smaller number, 1/2. And if I plug in x equals 2, I get 1/2 times 1/2, so I get an even smaller number, 1/4. Right, so as x gets big, we can see for this function, 1/2 to the x goes to 0. It falls down. On the other hand, our blue graph clearly shows us that when x gets big for that one, so 2 to the x, that will just go up and up and up forever. In fact, these properties aren't just for a equals 2 or a equals 1/2. These properties are also for any positive base. So if this were a equals 3 to the x, it would still be going off to positive infinity. Okay, so all of that's supposed to be kind of a quick review. That doesn't mean you're supposed to feel like an absolute expert. It's just the words I'm saying aren't supposed to be crazy. What we're really after is this fantastic, wonderful fact. The derivative of e to the x is, in fact, one of the easiest derivatives to take. It is the function e to the x again. This is a wonderful, amazing fact. This kind of makes the function e to the x feel a bit like the function 0. Right? When you take the derivative of the constant function 0, you get the constant function 0 right back. E to the x is just as easy to differentiate. Okay, so I want to encourage you, if you have time and if you're like me in this very stressful world we're currently living in, if you currently need some therapy, I personally recommend thinking about some math. It's a great way to distract your mind. So you might want to think about, why is this true? And if I have time at the end of this video, maybe I'll say a few words on how we can understand that this formula happens. But if I don't have time to put it in this video, please feel free to Google around and look on YouTube. There's lots of fun, excellent videos that discuss why you might believe this and how amazing it is. Okay, so let's practice using this new derivative rule, because it's so straightforward to do. So let's try, I'll switch back to blue. So example 1, if we're given a function like y equals 10 times e to the x, then dy dx, I can leave the 10 out front, and I'm just going to take a derivative of e to the x, and I say that's ridiculously easy. It's e to the x all over again. Okay, this one, example B, is a little weirder looking. So let's see. G prime of x. Let me just focus on this first piece, e to the square root of the sine of x. So this is the one we're going to focus on first. So I've got to put a prime there. And then I'll have to come back, and I'll probably, because I'm using such a large marker, I may not have room to do that second piece. Okay, but this first piece, we're going to treat this as a chain rule, right? The function that's quote-unquote on the outside is e to the blank. So that's the first thing we differentiate. So what's the derivative of e to the blank? It's e to the blank all over again. All right, so that's e to the square root of sine of x. And now I've got a times by the derivative of that blank stuff. And so now, let's see, I'll pick up on e to the 10 over x. This will be, again, we're going to take a derivative of the outside function. The outside function is e to the blank, and that's wonderfully easy to differentiate. That's e to the blank, and the blank here is 10 over x. And now I've got to multiply by the derivative of 10 over x. And I've clearly not left myself enough room to do this. That's okay. I'll pick this up on an additional page right here. So let me throw in an additional page. Okay. So we're picking up example B. What was that, 1B? And so what we have now is g prime of x was equal to e to the square root of sine of x times the derivative of the square root of sine of x. And I'll rewrite the square root of sine of x so that it's a little bit easier to differentiate. That's sine of x to the 1/2. And then our other term was e to the 10 over x times the derivative of 10 over x, which I will write as 10 times x to the -1. So now I'm ready to differentiate those other pieces, and I'll get e to the square root of sine x times, okay, so to take a derivative of the square root of sine x, I got to use a chain rule again. I bring the 1/2 down, leave everything inside alone, to the 1/2 minus 1, and then times, finally, the derivative of sine of x. This last piece, I'll have e to the 10 over x times, and the derivative of that stuff inside, that's going to be -10, bring the -1 down, x to the -2. So that's going to finish example 1b. All right, so this stuff of differentiating square root of sine of x and differentiating 10 over x, that should feel like an annoying but familiar review process. The new part here was the easiest part of this problem, differentiating the e to the stuff. Okay, so here's another example where we're going to probably use the product rule, example C. So f prime of x will now equal, and I'm going to take derivatives of this stuff. Let's see, so that's going to be 12x squared times e to the x squared. I'm going to write it like that. Plus 4x cubed times the derivative of e to the x squared. All of that's getting differentiated. So I'll have 12x squared times e to the x squared plus 4x cubed times. Okay, so to take a derivative of e to the x squared, I say the outside function is e, so the derivative of that is just e to that stuff, and then times the derivative of x squared. That's our chain rule. All right, so there's just a little bit of cleanup here. This will be 12x squared times e to the x squared plus that derivative of x squared is going to be 2x. And so let me just make a little comment here. This will be equal to 2x. And so when I do 2x times 4x cubed, I will get 2 times 4 is 8. X times x cubed is x to the 4th. And I'll have another e to the x squared. So for the purposes of this example, this way of leaving your answer is totally fine, but I want to keep us trained and focused on simplifying these expressions as much as we can. So for example, I see here, if I were going to use this derivative and like set it equal to 0 or something, I could factor out a 4 and an x squared, and I could factor out an e to the x squared from all of those terms. So what would I have left? I would have in my first term, I would have a 3. And then in my second term, I would have a 2x squared. Okay. Those are sort of terrible examples, I think. Example A is a good one because it keeps us focused on taking a derivative of e to the x. Examples B and C, I think, are kind of terrible because taking the derivative of the new stuff, the e's, becomes a really quick step, and the focus of this example becomes all the other stuff. And all of this is supposed to be about e's. But oh well. Since I have some space up here, before I do their example 2, let me try my own sort of generic example. I'll call this example capital A. And mine's going to be a little more abstract, but it's going to be kind of easier to think about. Suppose you have a function g of x, and it's e to a function of x. This is very much like examples, some of the pieces of examples B and C. Then the derivative of g of x, right? We're going to take a derivative of this composed exponential thing. We say, okay, first I take a derivative of the outside function. Well, that's just e. And then I multiply by the derivative of the inside function. Right, so, if I make another example, example B here, I could say, well, what if I gave you something like the previous examples, but not quite as ugly? G of x equals e to the, I don't know, sine of x, not a square root of sine of x. Then g prime of x, and this is a great place to pause the video and see if you can work this out, and then unpause it and see if my work matches yours. Okay, so this would be, take a derivative of the outside function, that's e to the stuff, times the derivative of my inside function is sine, and the derivative of that is cosine. So if you want to rearrange this, you could write this as cosine of x times e to the sine of x. I don't know which way looks better to you. But okay, those are some extra examples. Here's an example that we could totally do example 2, but before we do it, we should probably simplify it, because if I first start trying to take a stab at differentiating this mess of e's and e to the 2x's and a sum and a fraction, I'm going to use quotient rule and a whole bunch of rules. But keep in mind, we can rewrite this example as f of x equals, this is e to the 2x over e to the x plus e to the minus 2x over e to the x. Okay, so this first fraction that I wrote down, what I really have up there, that's e to the x times e to the x, if you really think about it. Right? Because what's going on with that first piece, that is our old exponent rule. When you multiply two expressions that have the same base, you add their exponents. So e to the 2x is the same thing as e to the x plus x, and that's the same thing as doing e to the x times e to the x. The benefit of doing this is that I can cancel an e to the x and an e to the x. Similarly, my other term, it has a negative exponent, so I can write that as 1 over e to the 2x times e to the x. And if you want, I can write that as 1 over e to the 3x. All of this was given to me by using exponent rules. And if you want, I can actually say, wait a second, that last term, I can simplify f of x. Yeah, I can leave it as 1 over e to the 3x, or I could write it as e to that negative power. Right, so this giant, weird-looking fraction, if we just remembered some exponent rules and how negative powers work in exponents, then we have a much simpler version of the same function, and so now its derivative is a lot easier to take. That's going to be the derivative of the outside function is e to the blank times the derivative of negative 3x. And I'm assuming everybody remembers that the derivative of negative 3 times x is just negative 3. And so this is a great final answer. Oh my gosh, look at example 3. Why are they doing this to us? Well, I'm pausing on example 3 to think about the best way to handle this one. Let's see if I want to handle it some particular way. Sure. So, sorry, I had to stare at this to really think about it. So, this question, they want you to take a derivative of this ugly-looking fraction, and you can totally do this without, I'll even write what I said, you can totally do this without simplifying this terrible fraction. So you could carefully use the the quotient rule and differentiate the numerator and denominator and then simplify your final answer. But there is a great way to simplify this. And so it took me a second to remember it. So here's what I'm going to do. Maybe I should switch to a less clunky thing. So I've got f of x equals e to the x plus e to the negative x all over 1 plus e to the 2x. So this little trick that I'm going to do here, it's not much of a trick, but if you are going to watch it and if you're going to be one of the people who say, hey, I would have never thought to do that, then that's okay. You could have hacked this through using the rules. But here's what I'm going to do. I'm actually going to leave the numerator alone. And from the denominator, I am going to factor out an e to the x from every term. So that second term in the denominator, it has 2 e to the x's, right? Because that's an e to the 2x. So when I multiply this e to the x against that e to the x in the parentheses, I will get e to the 2x. But it's maybe a little weird to think about taking an e to the x, factoring that out of a constant 1. But if you really think about it, what should go here should be e to the negative x. And I'll just sort of comment off to the side here. What I'm using is that e to the x times e to the negative x. Remember, we add the exponents when we have a common base. That's e to the 0, and every base to the 0 is 1. So once you rewrite this way, you quickly learn that f of x looks like 1 over e to the x times e to the x plus e to the negative x, all divided by, I'm going to rearrange the bottom a little bit, e to the x plus e to the negative x, so that the entire numerator is canceled by the entire denominator. And this function was really just a silly way of writing 1 over e to the x, and you can rewrite that as e to the negative x. So this really isn't a calculus question, even though it totally is. It says, here's a function, find its derivative. That's totally a calculus question. But to really get this done in a way that doesn't seem annoying, it's really an algebra question, right? You use a bunch of algebra to rewrite the function, and then you can do the calculus really quickly. F prime of x will be e to the negative x times the derivative of negative x. And so that'll be negative 1 times e to the negative x. And we could just write that as negative e to the negative x. Okay, so the sort of last part of these notes handles this situation. What if we're trying to take the derivative of an exponential function, but it's not the exponential function? What if f of x isn't e to the x with a natural base, it's f of x equals some other number a to the x? Then how do we do the derivative? And it turns out that this formula is what you get. The derivative of a to the x. It is almost a to the x. But you have to multiply by this weird constant, where the natural log of a, right? I just gave it away. This is what's called the natural log of a. And the point of this is the inverse of, let me undo that. Right? The natural log function is the inverse of the exponential function, e to the x. This is why section 4.1 was about inverse functions. Okay, so let's just practice how this rule is going to work. So for example 4, right? And again, this is a great one. 4a is a great one. The function is 5 to the x. We want to practice this rule. If this were e to the x, we would just do the derivative very simply. It would be e to the x. But you might want to hit pause at this point in this video to practice this rule. So if you've unpaused now, y prime, well, it's going to be 5 to the x times the natural log of 5. Right? A is being played by the number 5 in this example. And you might be a little annoyed or stressed or something, thinking, wait, I don't know what the natural log of 5 is, and that's totally fine. You just leave it written as the natural log of 5. All right, let's try this rule for part B. the derivative of this function, well, this is really, right, this is 4 to a bunch of stuff. So in this example, the number a equals 4. And so the derivative is just going to involve a chain rule mixed up with our new rule. This is going to be 4 to the stuff, whatever this inside stuff is, times the natural log of a, times, here's the chain rule part, the derivative of all that stuff. And so when I go to plug that in, that'll be 4 to the x cubed plus x, all of that times the natural log of 4, times the derivative of that stuff, that's x cubed plus x, all differentiated. So if I want to write that out a little bit more, that's 4 to the x cubed plus x times the natural log of 4 times 3x squared plus 1. Okay, let's try example C. I'm going to say g prime of x is the derivative of x times 2 to the sine of x plus x times the derivative of 2 to the sine of x. So this was just using the product rule. And really, only for one part of this product rule are we going to be using our new exponential differentiation rule. Right, the derivative of x we know how to do, that's just 1. So that first piece just becomes 1 times 2 to the sine of x. And that second piece will have plus x times, and this is where we're going to use our new rule. A is the number 2 in this example. It's not e, it's 2. And so the derivative of a to the stuff should be a to the stuff times the natural log of a times the derivative of all that stuff. Oh my gosh, this is my son. Liam, come here. Here, do you want to tell my students hello? They'll be able to hear you. Just speak right there. Say hi.
Hi.
Okay, thanks for the Coke. All right, hello? All right. So, this function ends up having an ugly looking derivative. It looks like 2 to the sine of x, and I wrote a bunch of a's there, I realize. Each a is 2, plus x times 2 to the sine of x times the natural log of 2, and the derivative of sine is cosine of x. So that's an ugly looking expression, but really what we're showing when we differentiate and get those two underlined terms, we're showing that we knew how to use these new rules in combination with old rules. Okay, so look, example 5 is kind of a great one because it's mixing up this new stuff, sorry for switching around, with our old things of talking about increasing and decreasing. Right? Now we're giving ourselves access to these new functions, these exponentials, and so we can ask these questions that we were asking about rational functions and trig functions, these questions of increase and concavity. We can ask them about these new functions that involve a to the x's. So here's an example of one of these. The function is f of x equals 1 minus e to the negative x. And one thing to quickly note, this function, its domain, is all real numbers. And that was part of our quick review of exponentials. Right, you can plug in any number you want as an exponent. Okay, but let's first see where the function is increasing and decreasing, and to answer that, we'll take a derivative. F prime of x, well, the derivative of 1 is 0, so it's just going to be 0 minus the derivative of e to the negative x. And so I'm going to have 0 minus the derivative of e to the negative x is e to the negative x times the derivative of negative x. And the derivative of negative x is negative 1. So when all the dust settles, I find that a nice formula for the derivative here is negative e to the negative x times negative 1. Those two negatives cancel, and I'm just left with e to the negative x. It's really easy to see how right up above over here, it's easy to make a sign error. So just keep a lookout for keeping track of all these negative signs. In any event, once we have this for our function, right, we want to figure out where is this derivative positive, where is it negative, and we answered that by first looking for critical numbers, which is where this number is 0 or doesn't even exist. For this one, though, we can note that e to the negative x is always positive, right? E to the negative x, this is e to a number, right? You could also think about this as 1 over e to the regular x. And in it, however you're thinking about it in this expression, e to a power is always positive. You're taking some positive number and multiplying it against itself x times, or in this case, multiplying it against itself x times and then doing 1 over that. But this is always positive. And so what we find are there's no critical numbers, and in fact, f prime of x is strictly positive everywhere on the interval from negative infinity to infinity. When we go to take the second derivative, oh, sorry, I should use the language that the question asked for. So this tells us f is increasing on this interval. And let me change that arrow that I made, lovely as it is. This tells us that. The second derivative is what tells us about concavity. And if I take a derivative of e to the negative x, if I do my chain rule correctly, I'll get negative e to the negative x. And this expression is always negative. Why is negative e to a power always negative? For pretty much the same reasons we just discussed above. E to a power is always positive, so you stick a negative in front of it, then that always positive number is always negative. So this tells us f double prime is negative everywhere, and that tells us our function f is concave down on this entire interval. So I'll try and circle these in a different color. So this statement and this statement answer the questions from this example. All right, so here's one for you guys to try yourself, but I will just put in here some important summary of all the sort of stuff we did. Really, this section of notes is actually pretty short. There's really one derivative rule that's going on here, and that is that the derivative of a to the x of these exponential functions is a to the x times the natural log of a. This is actually the one rule you want to really memorize from this, because if you have this one memorized, if you plug in a equals this natural base number, e, 2 point blah 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 blah, then our formula becomes the derivative of e to the x equals e to the x times the natural log of e. And I just want to point out, I'll put this out down here, that the natural log of e is 1 because natural log and e are inverse functions. So let me comment on that here. The natural log of e to a number, let me write this of e to the x. These two functions undo each other, so that's x. And so the natural log of, the natural log of e, well, that's just the natural log of e to the 1. And so those two functions undo each other, and I just get 1. And that's what happened right here. Okay, so it turns out the rule that I wrote down in green is going to be the one that it feels like you have to work to memorize. You're going to get so used to differentiating e to the x's and e to the blanks that it won't even matter. You'll just naturally know derivative of e to the x is e to the x. It's when we throw in a different base, like 5 or 7, where you might struggle to be like, oh wait, how do I do the derivative of a to the x? So practice the green one, it's a little weird. I am not going to include a discussion for this video on how to think about why the derivative of e to the x is itself, or why the derivative of a to the x is almost itself. Maybe I'll post a free extra video on that, but if you're impatient or curious, go look it up. Alright guys, have a great time. I didn't include a popper in this one, that's okay. I just wanted to get this video out there. Alright, I'll talk to you guys soon.